Okay, so now it's time to learn what the auxiliary variable metatheorem says. And we already know, or I already mentioned in the previous video, that this is the metatheorem that allows us to remove the existential quantifier in our proofs. So notice that this is not an automatic thing that we can do. If we know that there exists XA holds, for example, or we're assuming that it holds through a hypothesis, then we know essentially that there exists some x where A holds. But we don't know that A holds in general. So removing an existential quantifier is not so easy because it would say that A would hold for any x. So we need some conditions under which we can remove that existential quantifier. And so the auxiliary variable metatheorem, although it's not so bad to apply once you get it, at first it might seem a bit complicated. So let's go through it step by step. Okay, so the first thing is that we need to assume that gamma proves there exists XA. Essentially what this is that we have there exists XA somewhere in our proof. And we want to know how to be able to remove that existential quantifier to apply a result of Boolean logic, move things around, and then we would apply the dual specialization to add it back in. So if we assume that gamma proves there exists XA, so there exists XA approved somewhere in our proof, then, moreover, if we know that if we add in what we call an auxiliary hypothesis, so we add in a particular instance of A into our proof as a hypothesis, and with that addition of that hypothesis, we're able to prove a statement B, where here note that Z needs to be fresh with respect to gamma. There exists XA and B, so if we're adding in a particular instance of A where Z is fresh with respect to everything we are using in our proof, or that we're trying to prove, and adding that additional hypothesis allows us to prove B, then the auxiliary variable metatheorem says that we didn't need the hypothesis, that gamma proves B. So essentially what's happening here, and the use of the auxiliary variable metatheorem, is that if we have there exists XA occurring somewhere in our proof, then we're allowed to remove the existential quantifier and add in a particular instance of A with respect to Z, where Z is fresh with respect to our hypothesis, the well-formed formula there exists XA, and also the formula B we're trying to prove. So we're allowed to add in this hypothesis. Then if that allows us to prove B, then we can conclude that gamma proves B itself. So simply the auxiliary variable metatheorem gives us this auxiliary hypothesis to use to prove B. Okay, so hopefully that makes a bit of sense. I think it'll become much more clear when we look at a particular example. But before we look at a particular example, there's one very important note we need to talk about, and then we'll look at this a little bit more in class. So when we're using the auxiliary variable metatheorem, we're adding in this auxiliary hypothesis, A, where we replace X by Z. So this counts as a hypothesis. In particular, if we want to use weak generalization, remember that we can only apply weak generalization and add the quantifier with a variable that doesn't occur free in any of our hypotheses. So for example, if we use this auxiliary hypothesis in our proof somewhere, we're not going to be able to quantify over Z, for example, because Z occurs free in this hypothesis. Okay, so we have to be a little bit careful if we want to apply weak generalization in an auxiliary variable metatheorem proof. Okay, so now let's look at one example to give you a better idea about how this works, and then we'll look at more in class. So here is the statement of the auxiliary variable metatheorem to help you remember it as we're going through the proof. So remember, we know that there exists XA occurs in our proof, then we add in this hypothesis and we prove B, and then this says that we could have proven B all on our own. So this simply allows us, this auxiliary variable metatheorem simply allows us to drop this existential quantifier and add in this auxiliary hypothesis. Okay, so let's prove the following relative theorem. So we have for all x, A implies B, and there exists XA as hypothesis, and we want to prove there exists x, b. Okay, so essentially, you can see this hypothesis here has an existential quantifier in it, so we're going to list this in our proof, but then we're going to want to drop this existential quantifier, insert in our auxiliary hypothesis, and try and get there exists xb in our statement here. So let's see how this works. So consider, if we have hypotheses, what are the first steps that we need to do? We use those hypotheses. So we first list our first hypothesis and then our second hypothesis. Now we want to apply the auxiliary variable metatheorem, right? We want to remove this existential quantifier. So the auxiliary variable metatheorem says that if this appears in our proof, let's add in our auxiliary hypothesis. So we're simply going to add in this auxiliary hypothesis. We have to cite that we have an existential quantifier occurring with this particular formula in our proof, and then this is the one that acts as our auxiliary hypothesis. And we need to note that z is fresh here, right? Z can't occur in, this means here, here, or here. And again, we have infinitely many term variables, so we can find such as z. Okay, so now notice that we have a particular instance of A here. Now remember that we also want to use this hypothesis. But we really want, right, in the same case as before, we really want to get rid of the quantifiers, then use Boolean logic, and then put them back in as we need, right? So we're going to be able to add in an existential quantifier, but we need to get to B first. So remember that we have specialization, which allows us to drop this universal quantifier. However, we don't just want to have A implies B, right? We want to get B, of course, but we don't have A itself. We have one particular instance of A. So in this case, we want to use the actual specialization, which gives us a particular instance of A implies B. So we're going to get A implies B with respect to this particular substitution with this particular Z we have here. So notice that A implies B with that substitution, the way substitution works is we apply it over the connective here. So this is simply applying specialization to 1 and using the definition of substitution to distribute our substitution throughout. Now notice that we have an implication and we have the hypothesis, so we can conclude the conclusion here using modus ponens. So we get a particular instance of B. But remember, with the dual of specialization, if we have a particular instance of B, that means we have there exists xb. So by 5 and the dual of specialization, we get what we want to prove. And so simply the auxiliary variable metatheorem tells us that this is a valid proof here, because when we use this existential quantifier to drop it, we replaced it with this auxiliary hypothesis. So that's how the auxiliary variable metatheorem works. Hopefully that makes the process a little bit easier. We'll have an opportunity to do some more in class, and you'll have an opportunity to try them as well. Okay, and finally, we just have a couple of crawlers, a couple of different cases. So in the event that we don't have any hypotheses here, if there exists XA is simply an absolute theorem, then we can still use the auxiliary hypothesis, and if we can prove B from that, then we get that B is an absolute theorem. In the same way, maybe there exists XA is simply a hypothesis that we don't use in our proof. If we have this as a hypothesis, we could just jump straight to using the auxiliary hypothesis from this hypothesis, and if we prove B from that, then we have proven the relative theorem that we were asked to prove. So those are just a couple of special cases of the auxiliary variable method.